space weather have always been exciting, and only like been like several more, exciting storms since then. So pretty much the overall content of the talk is, what I've discussed of the Johnson Space Astronomy Club. And it's actually an exciting time. The reason is, the sun goes through this solar cycle every 11 years or so. And we are actually quite near the peak of the solar cycle, which is the solar max. We're going to be hitting the max in a couple of months before it actually wanes off, and then it dies down for another 6 or 7 more years before the new cycle starts all over again. So you're at the right time. So we're getting a lot of these storms coming through every week or every 10 days, keeping us busy and trying to understand more things as sun throws up all this major storms it does. So that's why I want to bring this picture right away. And the good thing is, everybody is picking up on this news these days. This is like a whole collection of stuff that I've been, gathering around, all around the world, see how people are interested in, getting to know about solar storms and space weather in general. So LA Times here, talking about radiation raises towards NASA spacecraft. There's another article from the USA Today. Pretty much all the last few years. USA Today talked about satellite capture, about the eruptions on the sun. And thanks to major missions like Solar Dynamic Observatory, or the SDO mission, the flagship mission for NASA. More, back home from the Hindu, it's like national newspaper from India, solar storms threaten high-tech civilization. And then again in Nature, astrophysics prepare for the coming space of the storm, and even more recently, radiation risk. This was something that talked about way back in 2001. So people have been talking about it a whole lot of time, but it's been getting all this traction only in the last few years. More recently, not ready for a solar Sandy. So it's good that the awareness has been growing all the time. When we read more reason to get more money from NASA or NS to do more, this kind of research. But it's an age-old science anyway. We can even go back to the mid 19th century when people were still using telegraphs and telephones as the basic way to communicate. And in fact, this was even at its infancy. We're talking about during the 1840s when this gentleman named W.H. Barlow, he's a British civil engineer. He used to design a lot of these rail bridges and a lot of things to do with railway construction projects. When he was using all these instruments back days, he wrote this comment on one of those journal publications talking about spontaneous electric currents being observed in the wires of the electric telegraphs. And soon after that, you have folks like Carrington. Richard Carrington is another British amateur astronomer, and he's like one of the earliest guys who did some original work and trying to see how much solar storms is doing damage to a lot of these kind of things. So it's the previous article kind of nicely predicts this, setting up the nice stage for later things to happen. So what Carrington did was he's a basic astronomer. Before astrophysics became a major science. In those days, people were just managing basic observational. They were just taking data from whatever they saw, using basic mathematics as a tool to develop more science. And this is what he was doing. Carrington did this nice graph where on the x-axis on this horizontal scale, it's just each day as it progressed. And you would go out and observe the sun, see what sun's doing, and then you would plot as to whatever you see from this image, from this solar telescope. And this is what he'd been doing. He would actually make a drawing of the actual surface features that you would see on the sun. And spotting everything, you would map it as the way you would map here. So this is 180 degrees, which is kind of the equator, and we have the northern hemisphere and the southern hemisphere of the sun. So this is exactly what he was doing, which gives you a good feeling, and then science developed more towards from observational to analysis and all that, but still you still do the basic observation. And this is exactly what happened. Once Carrington started doing it, we started doing the same thing. And we can even go back all the way back from 1850s to until now. And this is what people have been doing. This is the exact same slide. Now looks more, telltale sign or a clear picture. What is it telling? And solar physicists call this as the butterfly diagram because the way it looks like a butterfly. What you basically do is you actually map looking at the sun observationally and then do it. So this is all you get. Now the quick thing that actually jumps out of you is that every now and then there's a peak here. Every now and then there's a peak, and there's really nothing, and then there's nothing, a peak here, which actually correlates nicely. This is exactly the same plot, but done in a different way. In that people count the number of sunspots, and then they do it over an average of over a period of a year, and then do this plot. So it's a nice correlation between this and this. Now also one thing jump out on you that there have been like few years when the peak has been really high, and then you have so many other years when the peak has not gone to that distance, right? It doesn't mean that people are taking like that, bad data back in those days. It's not true. It's simply that sun behaves like that. It's just very simple. Sun doesn't know how it behaves. That's the challenge here. So sun can act like one time can go really up, like the last solar cycle. And this solar cycle, for example, is not doing so much as the last solar cycle. Luckily, it's nice for us. So this is the whole story. One more thing before we move on to the next slide is, as you can see, it's more, concentrated towards the equator. So sun's equator is where most of the activity happens. If you have a solar flare, or if you have a CME or anything that's coming out, it's mostly going to be located around the equator of the sun. So that's why it happens. And plus, as you can see, it's getting dragged on to one side, right? So this entire picture is getting dragged onto one side. So again, what sun does. Sun's rotation axis varies. Sun around the pole rotates slower than it rotates around the equator. It runs faster because sun is a huge ball of gas. It's not like Earth. It's not a ovoid. It's a huge ball of gas. The gases rotate differentially. So around the equator it rotates faster than it rotates around the poles. There's three-day difference. There's a 3-Earth-day difference between the rotation period between the equator. So that's very evident from this picture.
Doctor,
yeah.
On the last slide, we're at the 11-year sunspot cycle.
Oh yeah, sorry, I forgot to mention that. So
this graph shows a cycle, right?
Yeah, the graph shows a cycle. The peak is every 11 year. The peak is 11 year.
Right.
For
From one side of that to the other, you've got a rise and a fall.
Exactly. So that's the strange thing. What sun does? Sun is not very clear because that's the excitement we have. So physics.
Part of another cycle.
Yeah, it always varies. It's hard to predict that. That by itself is a different science. As I said, like this ongoing cycle is the solar cycle 24. Solar cycle 24 is not as bad as solar cycle 23. From my own experience, doing all this, data comparison over the last 20 years or so, this cycle has been far more quiet, and we're happy. Really grateful to that. This slide has nothing to do with solar physics or space physics. It's just a way to facilitate some communication between us, because more often, in the later part of my talk, I'm going to be talking more about the energy of the particles that beams from the sun. At the same time, I'll also be talking a lot about the different wavelengths. So this is by far the single most important slide. It contains the entire universe in this one slide. The good thing is you have a visible radiation which happens in only in that range. The bandwidth is so narrow, that's all you can see. The things that you can't see exist everywhere, right? So that's why we have instruments which can do things which we can't do. And as you can also notice on this energy scale here, it jumps every order of magnitude across the scales. It's 10.6, 10.5, 10.4, 10.2, 10. So it's every single order of magnitude. And as you can see, when you're talking about X-rays or ultraviolet, you're talking about extremely high energy. When you're talking about radio or infrared, you're not talking high energy. So that's something I just want to convey that before we move on to the next one. So let's see what the different compositions of sun looks like. Starting from the photosphere, which is where the light comes from. So it's pretty much what you see is what's there. It's by far the coolest place on the sun. It's 5,800 degrees Kelvin, ancient Celsius scales, which is roughly about 6,000 degrees. It's not too hot. And then of course you have cooler spots in the photosphere, which is what we call the sunspots, the darker spots. By no means it's darker, okay? It is brighter. It's just the relative brightness between the rest of the sun surface compared to that spot. We call it spot. So otherwise it's equally as bright, right? But the temperature is lower because of the magnetic field changes there buried underneath. That's why it's cooler. But it's still going to be bright. Now the next layer that's sitting on top of the photosphere is called the chromosphere. Chromosphere is something you can see, which actually exists towards the infrared of the spectrum, right? So it's quite close to H alpha. That's why it's H alpha. H alpha is, even with the solar telescope, you can go out via H alpha filter, you look through it, and this is what you see. Because you cut out the white light, and this is what you see. Gives you another perspective for that. It's mainly hydrogen alpha spectrum. The temperature slightly higher than the photosphere. It's about like roughly about 10 to 20,000 degree Kelvin. And what you see, the hairy feature on top of its head is just a prominences that actually sits on top of the surface. The next layer, I mean, the chromosphere itself is about like a couple of thousand miles. It's far thicker than the photosphere. The photosphere is a very thin shell, actually. So what sits on top of it is what you call the transition region. The reason that you call it the transition region is because it sits in between the corona of the sun and the chromosphere. Okay, the corona is a whole new level of surface in that the temperature between the photosphere and the corona increases by about like 1,000. So it's a huge order of magnitude difference. Okay, so that's why you have a layer that actually transits. It's being heated on top by the corona, and it's also have a cooling effect because of the photosphere. Somewhere beneath it sits the transition region. So most of the solar flares happens from the chromosphere. So things change, pictures change, but mostly what happens in the flares happens from the chromosphere because it's extremely thick flare. It's got a lot of material that it can dump. So that's what happens. So that's why you call this transition region. And again, this is not going to be visible. This is not in the visible region. Again, this is the X-ray image. This is the X-ray image. Again, the hotter you go, you're no longer going to have hydrogen, or you're not talking helium. The simple element doesn't matter because it's extremely ionized, because you're going to strip off all the electrons so easily because of the heat. You're literally talking like hundreds of degree Kelvin here. So it's at least 10 orders of magnitude higher than the photosphere. Okay.
Is the only one that's visible to us the first one?
Yeah.
Okay.
So you're trying to do some kind of synthesis to actually look through a different instrument to actually get this image. But this by itself is the X-ray image. The last the outer layer of the sun is the most exciting thing for us, which is the corona. Sorry. It's about 1,000,000 degree Kelvin, 1,000,000 degrees, can you believe? And even the interior of the sun, which is the fusion happens, the interior of the hand, even that's 15,000,000 degrees, so it's extremely hot. So this is where most of the activity happens, and this was an image that was taken when we had like solar eclipse. The good thing, this is astronomical coincidence, like you can actually cover the entire disk of the sun because the distance where the moon is located, it has the same angular diameter, right? So that's like a nice coincidence in astronomy. So this was taken during that time, and as you can see, you can have all these streamers going out from the corona. This is all like the features that you see in the corona, and you call this the helmet streamers. And you can also see these nice features kind of following a nice loop here. We'll come to that later. But this is actually coming out from the poles here. This is actually coming out from the southern pole here and along the equators. And this is like an average picture. Okay, this picture is not to be held true always. Things change a lot in the sun. This is just an average picture of how the corona looks. Things might happen in a flash. during a solar max and a solar min, it's a completely different model. But on an average, this is how the sun works if you cover the block the bright disk. And all the instruments later on use these technique. You know, people don't more want to see the flashy part of the sun. You know, I just want to study this corona. This is what they did. They built a telescope and put a disk on it in such a way that the angular diameter of my blocking disk would do exactly what moon would do for us during eclipse. So it's a nice thing. Now, before moving on, you know, again, like remembering like periodic table, like in chemistry class. So hydrogen and helium sits right there, and obviously they are more inert because it's more stable, and it's easy to strip off the electrons because just one electron, one proton, and helium have two and two. So it's much easier in terms of the physical chemistry. But as you move on in different orders, like, you know, then you have carbon and oxygen, which is far more complex, at least compared to hydrogen and helium. And then you have heavier elements like iron. I mean, this is where it gets tricky, you know. It also like tells you different where you can look for, you know, what part of the sun you can look for which elements. What part of the sun is going to give you this emission. So if you see this emission, what does it exist there? So if you see a cooler part of the sun, you're talking more in terms of hydrogen and helium. If you're talking the hottest speed of the sun, you're talking more like calcium and iron, like more you would see in a transition region. So that's one way to look at it. So this is, as I said, this is an image that is coming out from the Solar Dynamical Observatory, which went up in space back in early 2010. And, I mean, this is NASA's biggest solar missions ever. I mean, this has done a tremendous job in that you literally get high definition images of the sun, so never before seen. Okay, this is the best so far we've had. And interestingly, in that what you're really seeing here is the transition region, actually the lower part of the corona. Again, you're looking at an 171 degree angstrom. So this is not visible. This is ultraviolet image, and most of the emission that you see is going to be calcium and iron or something like that, heavier. Nothing lighter like hydrogen or helium. So what you see is nice arcade-like structures and loops. These are really getting ready to attack. You know, so it can go up anytime. But right before these emissions, all these active regions is what the space weather expert you're looking at. So as soon as these erupt, you want to know which way it's coming. Otherwise, you better run for the hills. So why do we care so much about solar physics, and why do we care so much about space weather? Because this is one of the things that we at Hawaii Space Institute do. I mean, we're actually kind of running a few models that actually responds well to the activity that happens in the sun. So we have ground-based instruments which are responding to the solar or storms, right? So, and we can actually read this instrument and give a feel of what's going on in the sun. So we have satellites which will give us this upstream solar wind conditions before it can reach us. So that way we can find a way to predict these things before it can strike us. So this is one of the things we're doing at Rice University. And see what happened like early last year. You know, you see all this red dots here. Red dots are actual observations, and the blue bars are the predictions from our models. You see there's a big discrepancy there. You have like a barren islands there. We completely missed it. You know, this happens more often than not. The reason is when sun gives us all the solar storms, it just attacks us all the way. I mean, there will be one storm after another storm after another storm. So within like 3 or 4 days, you can have 3 different storms which can actually attack some of the satellites that are meant to measure these things. So what you do then? You can't do anything. So this is where it gets tricky. So can you knock off any satellite or instruments that are actually measuring the sun? So this is a clear indication of why we need to have a firm understanding of space weather and solar physics.
Do they knock the satellite out permanently or temporarily?
Temporarily, but sometimes the sensitivity of some of the instruments can go down. I mean, it happens more often. I mean, you can even knock off completely. So you can have all sorts of problems. Sometimes surface charging, sometimes the single engine upset for a few hours. those kind of problems are so common, especially when a series flares happen. We'll get into that, like what kind of intensity is actually needed to do these things. But sun can do many things that we can't do. So that's why a weatherman is someone who will listen to you and you never believe. So what is space weather? How do you define that? The way to define that is space weather forecasting combination refers to efforts to monitor prevailing conditions at the sun, the solar wind. I'm going to talk to you solar wind in a second. The energetic particles of solar origin, and to predict changes in fields and particles in the Earth's magnetosphere and ionosphere. So you're talking all the way down to the ionosphere, starting all the way to the surface. Anywhere in this surrounding, you're going to have effects effect. Okay? So the origin, that's the sun. So close to where we live, ionosphere. So there's always plasma propagation along solar wind. So they're all tied together nicely. It's a nice video here, which will so this is a nice active region, almost on the southern tip of the sun, which is waiting to explode. Now what makes this science hard is because the geometry of this explosion and the direction is very hard to predict. We don't have any model that can actually do it. We can approximate, we have probabilistic forecast, but extremely difficult at this point of time to give you the exact geometry and the time and the direction at which way it's going to go. So that's tough. But again, now coming to the Earth, this is going to propagate into this, interplanetary space, and if we happen to be in the path, it's going to hit us. The nice approximation that one can imagine about Earth's magnetic field is, it's dipole field. It's just placing a huge bar magnet, and when you have a bar magnet like that, and you have an explosion that's coming at us, you will see this happening. You have the day side here, which is the sun facing side, and then the night side here. So everything is getting deflected off by the Earth's magnetosphere, and there's always a chance that some of them can enter through this cusp, through some merging here, which I'm going to talk to you later, and that's what is causing all the trouble. So about 80% is going to be deflected off because of the magnetosphere. Thanks to that, it's just that 20% is going to cause you a problem, and that's an enormous amount of problems, even that 20%. So the solar wind, okay, solar wind is the important thing because that's the way how it's going to propagate. The solar wind it's something you can easily imagine in terms of, imagine your garden hose to be your sun, which is sprinkling water. It does two things. You open the tap, it's constant flow, and then the sprinkler always turns at the same time, sprinkling around and the part. What happens is it makes kind of a nice angle, like a nice angle. That's exactly what sun does, because sun is throwing something at you. At the same time, sun is also turning, right? Now, it's not going to come straight at you. It's going to come in a direction of the magnetic field, because the magnetic field is the way how it guides. It's like a railway track. You cannot get out of the railway track. You just have to find this path, which is usually following the magnetic field. As I rotate, the magnetic field is still going to, so it's going to make this nice little angle. So anything I throw has to follow this loop before it hits you. It's not going to follow straight like that, okay? Now this is what happens when a solar wind blows. The sun is rotating. This is a model, computer model, okay? This is the sun, and you have the orbit of Mercury, Venus, Earth, and Mars is right around the edge here. So this is spinning at the same time the solar wind is flowing, which is going to take the path of the sun's magnetic field. Okay, the sun's magnetic field is basically the expansion of the solar corona, which we saw earlier. So anything that expands out of the solar corona will propagate along this field line coming to you in this direction. When it comes to you, this angle is somewhere in the neighborhood of 45 degrees. Okay? And that might change based on the situation of the storm, but on average, when things are quiet, it's going to be quite a bit down. No matter what happens, you cannot go in a straight line along the radial shore. It has to follow this path. So that's by definition of plasma physics. You can't violate that. So anything has to follow the path. But typically, what are the properties of the solar wind? Let's see that it's kind of very consistent with corona, so it's extremely hot. If you measure the solar wind, it's extremely hot object. It's supersonic, for 350 to 400 kilometers per second on an average, which translates to about like 3 days, maybe 2 days for it to reach Earth. If it's faster, it's faster. If it's slower, it's slower. But on an average, it's going to take 2 or 2 to 3 days to reach Earth. And it consists mostly of protons and electrons with traces of other heavy elements. Any plasma, when we talk in plasma physics, always easy approximation, protons and electrons. And obviously, electrons travel faster. The reason is it's more like 1800 to 1900 times lighter than protons, so it's much faster. But so when we have a proton and electron propagating through, depending on how fast it starts, it's going to reach at you at speed. So that will change based on the dynamics of what happens on the sun. If it's a rapidly moving solar flare or CMB, it has more energy to begin with. It's going to come at us at faster speed. But if it doesn't, it doesn't. Now this is another interesting picture. People were able to, compute the magnetic field as a function of time. You can also plot it as a function of distance from the sun. This was actual data coming from Voyager 1. Okay, Voyager 1 was launched in 1978. Now it has already crossed the termination shock, which is technically outside the solar system. So as Voyager was traveling across the solar system, it was sending us the data, and we were able to measure the magnetic field. And this was Parker, Eugene Parker was a big-time scientist in our field. He did a model of how it's going to look like, and this was his prediction. Actually, all the black line is his model, and then the black dots actually are from Voyager 1 data. And see how much nicely it coincides. So the fundamental property of the solar wind doesn't change. It just keeps propagating all the way to the termination shock, no matter what you want. So right from there, it's got so much energy. Solar wind has so much energy when it leaves the sun. It continues to go at that speed all the way. That's really amazing. If you're wondering how the sun can use that much energy, it can take you all the way there. So that's a nice thing. So basically what happens is the plasma drags the field with it, creating a pattern that looks like that. Okay? Now, before switching gears and coming to the Earth, here's a picture of what I call the kitchen sink shock. I mean, you just open a kitchen tap, and then water flows out, and then it kind of shocks you because this is the outer surface of your kitchen sink. So as somebody reaches the surface, it's finding it shocked because it can't go anywhere because it's not a free flow. It's getting blocked by the surface, right, making this nice little pattern around itself. Okay. Now you imagine the same thing that's happening between the solar wind and the Earth. Now here is your Earth sitting in the center of this picture. We have a nice force that's being exerted by the Earth's magnetic field, which is represented by the magnetic pressure. Now on the left side of the picture, we have a resisting force that's coming from the solar wind, which is basically the sun's force. So these two forces have to be balanced, and that balance happens somewhere along the flow shaft, which is similar to what picture we saw earlier. Now, these two magnetic field merges, making a pathway for everything to get into the Earth and into the magnetosphere to make things active. And this is what happens. So you have a solar wind flow making a dynamic, applying a dynamic pressure, and you have a plasma pressure, and the sun is applying pressure on that side. Now this distance is, this distance is approximately about 10 Earth radii, and that will change based on how force that will change based on how much force is being exerted on the sun, on the Earth by incoming CME. If the CME is extremely enormous, it's going to be compressed to all the way to about 5 to 6 degrees. So it has tremendous amount of pressure that can compress this distance. Now the tail can go as high as about 100 Earth radii, and can actually surpass the moon's radius, moon's orbital distance. So it's way out there. So the evolving story here is you have sun looking, observing missions like SOHO, RESI, SUO, Solar Orbiter, the rest. Voyager is something that was launched in the 1970s to mainly measure things as it went past the solar system. And then these are more recent missions. The TWINS mission, the RBSP, which is mainly studying the Van Allen radiation belt. You have the SINDI mission, which is mainly talking about like ionospheres. You have THEMIS, it's a cluster of 5 satellites, which is measuring the dynamic coupling between the sun and the Earth. And then the SUO mission is serving, it's non-stop picking data about a sun in several different wavelengths. At the same time, trying to get the underlying magnetic field mapping on the surface of the sun. So that's exciting. So it serves dual purpose, both for space weather and for studying solar physics. And Stereo was launched for like maybe 9 years ago. It's a pair, one orbiting in the opposite direction going around the sun. So that's a nice satellite. So this is pretty much what we've had in the last 15, 20 years or so, doing so much of work, and we still have plenty more to learn and do. This is a nice cartoon of, if I were to make all this